let's go ahead and begin. Hello, everyone. Welcome to today's webinar, which is part of the Private Water Network's Groundwater Treatment Webinar Series. Thank you for joining us. My name is Reem Tariq. I'm a Senior Project Coordinator at the National Environmental Health Association, and I'm also serving as the lead administrator for the Private Water Network. Before we get into the details of the webinar, I'd like to address a few things about the network. If you are not a member of the Private Water Network and are curious about learning what the network has to offer, then I'd be happy to inform you that the Private Water Network is a virtual community of public health professionals and safety workers that work with private drinking water systems. The network was launched by the National Environmental Health Association in partnership with CDC and the National Network for Public Health Institute. The mission of the Private Water Network is to build a sustainable community for those working to support private water programs, to connect with their peers, to share experiences, insights, and resources, and to gain access to timely, relevant guidance for existing and emerging issues, as well as to build capacity to do the work more effectively and efficiently in order to protect the public's health from contaminants in private drinking water sources. Membership to the network offers access to a virtual community platform that offers features which typically come with virtual communities, such as a discussion forum, a resource library, an events calendar, member directory, so on and so forth. Just so you know, this is a free resource to anyone who would like to join. We just ask that people be working with private drinking water sources in some aspect. With that, let's go on to our webinar series. So the Private Water Network is doing a monthly webinar on treatment concerns and options for existing and emerging private water contaminants. So far, we've covered contaminants such as arsenic and radionuclides. For this installment, we will be focusing on lead. And the title for today's webinar is Lead in Private Wells. This webinar will focus on lead treatment in private wells. Lead commonly occurs in private well water due to corrosion of household plumbing, or less frequently due to groundwater contamination. We'll discuss the occurrence and the causes of lead in well water, along with the corrosion control, reverse osmosis, and other treatment strategies. Our speaker for today's webinar is Bryan Swistock. Bryan is a water resources extension specialist at the College of Agricultural Sciences, Department of Ecosystem Science and Management at Penn State University. He received a bachelor's degree in environmental health from Indiana University of Pennsylvania and a master's degree from Penn State University. For the past 32 years, he has conducted research, teaching. Just a couple of housekeeping rules. Before we begin, this session is being recorded. The recording will be uploaded onto the Private Water Network resource library. We'll also share any links that might be referenced in this presentation in a follow-up email. And those links will also be uploaded onto the resource library under a folder on the library, which is labeled after the webinar series itself. Okay. Please use the Q&A box to drop your questions. We'll respond to all questions towards the end of the webinar, but you can drop your questions at any point that they occur to you. At the conclusion of the session, you will be directed to a short evaluation survey. Please do complete that survey. Shouldn't take you more than a minute or so because it does help us to plan for future webinars and just a general evaluation of the program itself. And with that, Bryan, I will hand it off to you, and let me stop sharing my screen so you can share yours.
Okay, thanks, Reem, and good afternoon, everybody. Let me just get my screen up here. and make sure you're going to be able to see everything okay. That looking okay, Reem?
Yes, looks great. Thank you.
Okay, thanks. So just a little bit about where I come from and who I work with, so you'll understand more about the data I'm going to show. I do work in Pennsylvania with Penn State Extension, so my background is been working with private well owners and private water system owners in Pennsylvania. And some of the unique features about Pennsylvania in that regard are that we have a very large population of those folks. We have about 1 million rural homes and farms that use private water systems. They're about 90% drilled wells, about 10% of them are hand dug wells, springs, and rainwater cisterns. And slowly but surely, we're getting more and more drilled wells, and the springs and hand dug wells are kind of going away over time. We also have some survey data that shows that a lot of people have never tested their water, certainly not properly through an accredited laboratory. And when we do testing, we find that about 40% fail at least one of the health-related pollutants, things like lead and bacteria and nitrate and arsenic are some of the example problems that are more common here in Pennsylvania, and I think are common in most areas. We are somewhat unique in that we have no statewide water well regulations here in Pennsylvania. So for that reason, we have people really doing almost entirely voluntary management in this state. Just a quick review about lead in private water supplies before we get specifically into treatment. As far as a drinking water standard, there really is no true drinking water standard for lead. It's got what's called an action level of 15 parts per billion, or 0.015 milligrams per liter. It is too often used as a MCL or as a health-based standard. So we use that 15 part per billion action level in replacement of a health-based drinking water standard. And it's kind of unfortunate because that's really not what it was ever intended for. And I was around during the great debates of the 1980s when the drinking water standard for lead was 50 parts per billion, and they were trying to decide what to make it. And there were a lot of people that thought the standard should be 5 parts per billion or should be 10 parts per billion. And they finally settled on the 15 part per billion action level, which is really geared toward municipal water supplies. And we really don't have anything better to use for a private water system owner, right? We don't have any true standard. We can use the 15 part per billion action level as a replacement for that, but it's important to realize that's not really what it is. There is a goal of 0 milligrams per liter, recognizing that lead can only do bad things. It has no good use in your body. And so any amount of lead can be damaging. And in fact, even levels as low as 1 part per billion can be a problem for very young infants. It is measured uniquely in what's called a first draw sample, where we measure water that has been sitting in the plumbing for several hours, usually overnight, to try to get at that worst case scenario of how much lead builds up from plumbing system corrosion. So it's unique. That and copper, lead and copper both have a first draw sample, which is different than pretty much everything else that we collect for water quality, where we typically would get a running water sample. The sources of lead, as Reem mentioned, there are occasional cases of source water contamination. Even naturally occurring lead can happen, but those are typically pretty rare, and I'll show you some data on that. The typical source is corrosion of household plumbing, and in Pennsylvania, corrosive water is the most common water quality issue that we run into. More than 60% of our wells and springs have corrosive water. The graphic down on the bottom right there shows that it even varies quite a bit by water supply type, where springs tend to be the worst because they have the most corrosive water. They tend to have higher lead levels. They also tend to be associated with older homes too. So springs are typically our worst case scenario, where we have the most corrosive water under the conditions where lead is present. Drilled wells are usually a little bit less of an issue. When it comes to corrosive water, it is extremely complex. There are different indices that we use. None of them are perfect, but there is what's called the Langmuir Saturation Index, or the LSI index that we use. It's a calcium carbonate saturation index, which basically looks at the nature of the water and whether it's going to deposit calcium carbonate or whether it's going to leach materials from the plumbing. And so negative LSI values indicate corrosion, and positive LSI numbers mean scale formation, where scale will be deposited in the pipes. There's also a galvanic corrosion index that we can use. The potential to promote galvanic corrosion, which is based on the chloride to sulfate mass ratio. This ratio became more popular and became more aware from it because of what happened in Flint, Michigan, because of increased chloride levels can cause more galvanic corrosion to occur. Alkalinity is also still important here, but chloride concentrations in relation to sulfate are really the main issue. And as I mentioned, high-risk homes tend to be those that have metal plumbing, specifically copper plumbing with lead solder, as is shown in the picture up there in the top right, that was installed prior to the regulations that went into effect that removed a lot of lead from solder, which took effect in the late 1980s. We often throw around 1990 as kind of a cutoff because we found that a lot of those materials were still used for a while. Even after the regulations took effect, plumbers were still using up old stock of lead solder. And so we often use 1990 as kind of a cutoff, where if a home was built prior to that and it's got solder in it, there's a very good chance that that solder is going to have lead. Lead also being in fixtures and faucets continues to be a problem, even in relatively new faucets. And we can talk more about that here in a moment. Now, as far as what we do to reduce lead, and we'll get into more details on all this, but obviously prevention is what we prefer to do. And the best case scenario is to go into a home that's got lead source in the plumbing system and remove that plumbing system and replace it with a non-leaded source. So that would be something like taking out old copper plumbing and using PEX or approved PVC plumbing in its place that will not corrode. We can also put in corrosion control treatment, where we leave the plumbing system intact, but we put in a treatment system that will make the water less aggressive toward the plumbing. And that's things like acid neutralizing filters, which we'll talk about in more detail, where we treat all the water coming into the home. We reduce the corrosivity of that water and make it non-aggressive toward the metal. The simplest treatment method, and if you want to call it treatment, is simply to flush the plumbing system and get fresh water out of the well, because it does take some period of time for lead to leach from the plumbing. And usually we throw around an hour minimum, sometimes several hours, before lead can reach appreciable concentrations as it sits in contact with that lead solder. So the idea is, if you just go to the tap, run the water and flush out all the plumbing and draw fresh water from your well, that you'll get lower lead concentrations. It assumes that you don't have lead in the source water, which again is a rare problem, but it will work very effectively if corrosion is the main issue. But it's a lot harder than it sounds, really. We have a lot of complexities with plumbing, the size of the plumbing, the amount of water use, exactly how corrosive is the water, how much lead solder is present. So it's hard to give people generalities about, okay, run the water for X period of time and you're going to be fine. And this gets really complicated in public water supplies, right? It's actually pretty simple for private water supplies, where you maybe just have a single home on a well. But when you get into large municipal systems with lead mains, or you get into apartment buildings with massive plumbing systems, that's where the flushing of the plumbing system can be much more problematic to try to avoid lead. And we'll talk more about flushing. I'll show you some data on that. Bottled water is an option, as is various treatment options. And the idea here is that since lead is basically just a drinking water issue, you're not going to absorb it through your skin, you're not going to inhale it, we can treat it at the tap, or we can use point of use treatment, things like carbon filters and RO filters and distillation units, or we can just use bottled water and avoid drinking the water. But we can still use the water for other things. It's not going to be harmful for clothes washing and for showering and bathing and so forth. So it is somewhat more simple in that respect, in that we can just remove it at a single tap and use that tap for our drinking and cooking. So we'll touch on all of these in a little bit more detail. I'm not going to talk more about bottled water, but bottled water is obviously an option if you're trying to avoid lead, assuming you get a good quality bottled water that doesn't have any lead issue. Now, what about lead in source water? So one of the first distinctions we always have to make with treatment is, are we dealing with a problem that is coming right out of the well, or are we dealing with corrosion in the plumbing system where the source water does not have any lead? This has been challenging in the past because for a long time we had problems with lead corrosion even down in the well, and we still have a little bit of that, but there was a time when some of the submersible pumps had lead impurities in the actual pumps themselves. And so if you put that pump down into a well with corrosive water, it would slowly dissolve away the casing of that pump and would produce lead actually down in the well. And there were other metals that were used in the casings and in other components of the well that occasionally had lead impurities in them. So we have to distinguish how commonly do we find lead actually in the source water, because that's going to necessitate different treatment. We can't just use corrosion control or water system flushing. We would have to use some sort of removal strategy like an RO system or a distillation unit, because we need to treat the water as it comes in from the home, or excuse me, from the well itself. Now, there have been some studies here in Pennsylvania that have looked at source water contamination from lead. There was a large look at pre-gas drilling samples in large areas of the state. Over 11,000 samples were collected, and these were basically pre-treatment samples, so they would be ideally coming from the well itself, and they found 3.6% of those samples had more than 15 parts per billion of lead. So that's a pretty significant number. That indicates a more significant source water problem with lead than I would have maybe expected. Our lab here at Penn State has collected thousands of private water system samples. They are homeowner collected samples, which is an important caveat. And we never know exactly how the homeowner is collecting the sample. We give them instructions, but it doesn't mean they do it correctly. And in that large data set, we find that 3% have lead in running water samples. So these would presumably be samples where the homeowner flushed the water supply out. Now, again, did they do it properly? Did they flush the sample enough? That's always a big question. And then another data set is a USGS data set that's been looking at water wells in northern Pennsylvania. It has almost 500 samples now in 7 counties. And these were collected very professionally. Nobody knows how to collect samples better than USGS, specifically groundwater samples in this case. And in that particular study, they found that 0% of those groundwater wells had lead above 15 parts per billion, at least. Now, they did find some detectable levels of lead in other samples, but as far as having levels actually meeting the action level, it did not occur. So, I mean, my gut feeling and my perception of this is it's somewhere between 0 and 3%. I know in dealing with those 3% that have submitted samples to our lab that had running water samples, I know in follow-up with a lot of those folks, we found that they simply did not flush the sample long enough. And when we followed up and went through another set of samples where we flushed an extra period of time or looked at the pressure tank specifically and flushing of the pressure tank, we found that a lot of those samples turned out to not have lead in the source water. So I think it's safe to say it's a very rare event. I can really only think of a few cases that I've dealt with where we could absolutely say that lead did occur in the source water due to industrial contamination or due to some naturally occurring source of lead. So the vast majority comes from corrosion control, and this is what a typical water test report might look like. And I get these almost daily from our laboratory here, where you notice on here we have a pH of 5.99, so slightly acidic water. It's very soft water. It only has 23 milligrams per liter of total hardness. It's got a corrosion index, in this case, the Langelier saturation index of negative 3.05, which indicates a strongly corrosive water. You see that the running water copper was practically nothing, but the first draw copper was over 1 milligram per liter. Similarly with the lead, the running water lead was below detection, but yet it had over 100 parts per billion of lead in the first draw sample, the 0.106 milligrams per liter, or 106 parts per billion. So this is a very classic case, and we see samples like this all the time. Very, very clear indication that the corrosion of the plumbing is what's causing the problem here, because we have no lead in the running water sample, but we have lots of lead in the first draw, and we've got a very corrosive water supply. So one of the issues with treatment of lead in particular is awareness. And I've shown this graphic in other presentations that I've done, and it was really one of the most startling things that I've ever seen in my career in particular, was when we look at how aware people are of a water quality problem in their well. We know that they're very aware of aesthetic issues like hard water and iron and sediment, things that they can see or they can taste. Their awareness is very high. But things that do not cause an obvious symptom, their awareness is very low. Unless they test the water for it. And in this particular study, we tested 701 water wells across Pennsylvania. And in that study, we asked people before we tested their water, of all these different parameters we list, which of these do you know is already in your water? Before we even test it, what do you know is wrong with your water? And then we compared with what they knew was wrong with what was actually wrong. And that's what these percentages are reflecting on here. And the lead you see there is a 0. And in this particular case, out of the 701 water wells, 84 had lead above the action level. And when we went back to those 84 homeowners and looked at their surveys, 0 out of those 84 people selected lead as a pre-existing problem that they knew they had. So there was total lack of awareness of lead, which is not terribly surprising. It has no obvious symptoms other than the copper symptoms that you might notice. And it's not tested that frequently. At least it hasn't traditionally been tested very frequently compared to things like nitrate on this list, where there's more awareness because there's more testing. Similarly, bacteria, there's more awareness because there's more testing of that problem as well. So the big hurdle to overcome with treatment of lead is just, first of all, making people realize that they have a lead problem and getting them to test the water. And we see here in Pennsylvania, again, with our lab, based on the Ag Analytical Services Lab here at Penn State, over 13,000 samples since 2007. A little under 3,000 of those people chose to do lead and copper analysis, which is about 20% of all the samples. So these are people selecting to get their water tested, and they select what they want to have tested. And only about 20% select to do lead and copper analysis. And that's actually higher than it used to be. We found up until a few years ago, it was running closer to about 10 or 12%. As soon as Flint, Michigan happened, the awareness of lead increased and more people started asking for lead analysis, especially as part of home sales and mortgage companies and home inspectors. We started to see more people paying attention to lead, but it was maybe 10% or so prior to that that were actually testing for lead. So this is an important hurdle to overcome. You can't treat something that you don't know you have. And unfortunately, lead is such a serious health problem. It's one that you really have to make sure that you're testing for. And when we look at the percentages that are testing for other things, practically 100% test for bacteria, 40% test for nitrates and things like hardness and total dissolved solids and iron and manganese. Again, mostly aesthetic issues is what they're testing for. And they're paying much more attention to those than maybe to those health-related pollutants that really should be getting more attention, because testing is the only way that you're going to find out about them. And that is really important with this graphic, because it shows that 0% of these people before we did the study were aware of lead, therefore 0% of them were actually treating for it. And we even looked at their surveys and looked to see how many of those 84 homes were already just inadvertently using bottled water. So they were inadvertently avoiding the lead, even though they didn't know they were doing it, they were avoiding it. Or how many had an RO unit already installed, so they were inadvertently treating for lead, even though they didn't know it. And actually, in this case, none of those 84 homes had any kind of treatment or any kind of system in place to avoid the lead. But by the time we told them about it, 75% had taken action. They were using bottled water. They were flushing the water system. They were installing corrosion control or reverse osmosis or carbon filters. They were doing something. So it indicates there's a very strong interest, of course, in drinking safe water. That's a given. But that awareness hurdle has to be overcome mainly through the testing aspect first, and then we can start to match up the proper treatment. And we really spend a lot of time here at Penn State trying to make sure that people have access to this testing. We give out thousands of free or low-cost water tests. Right now, we're giving out about 650 tests every year to private water system owners in Pennsylvania. And on the public side, a lot of public water suppliers are doing the same thing with lead. They're offering free testing to their customers because lead is a big issue in municipal systems, because it's home by home. It's not something they can just test at their treatment plant and then tell the community what it is. It can be very different from home to home, and that's why getting everybody tested is really important. So the first thing to talk about, and it relates to treatment, is how important is treatment now and how important is it going to be based on the regulations that are in place and are happening to try to reduce lead. And so there have been a variety of different regulations passed. Back in the 80s, there was the Safe Drinking Water Act, Section 1416, which started to reduce the amount of lead in solders. It reduced the lead down to less than 8% in fixtures, and it's what came up with that action level. And so that was kind of the first step where we started to control lead in public water systems, and then also in private systems, because we started to reduce solders. There have been various tweaks to this, and there was a revision in 2011, which took effect in 2014, which started to redefine what lead-free meant, started to reduce that fixture level from 8% down to 0.25%. And so it started to kind of tweak the regulations to get better control over lead sources, even within fixtures, not just within the solders, which was a lot of what the original Section 1416 did. And so what we've seen over time are these regulations taking effect and reducing the amount of lead solder, reducing the lead in fixtures, so that even if you have corrosive water, we should theoretically be seeing less and less lead as older homes are renovated and they start to use different systems. So for example, the picture on the right is a PEX system where we have basically a tree, blue lines are the cold water, the red or the hot water. They all go out to a different tap, and it's a plastic type of plastic line which does not corrode, has no lead in it. And so this is what you see a lot in these new homes. Instead of the old copper pipes with what was lead solder, now we're moving toward a lead-free system where hopefully the fixtures also used have very little lead in them as well. So what we have seen as a result of these regulations is decreasing lead occurrence over time for the most part. This is private water system data, so mostly water wells, but also springs in Pennsylvania. The first study in 1988, if you look at the far left there, the percent of the samples in that study that were detectable above 1 part per billion of lead was 80%. So almost, again, 8 out of 10 homes that we did had detectable levels of lead. It dropped down to just over 60% in 2007. And then last year, the most recent data, we have about 40% that have detectable levels of lead. If you look out there at the action level at 15 parts per billion, it was almost 20% in 1988 that were above the action level. 2007, we dropped it down to 12%. The most recent data, we're down to about 9% now. So we're seeing a steady decline in the occurrence of lead, and theoretically this should continue as we continue to renovate old homes and remove the sources of lead and get the lead levels in fixtures and faucets down lower and lower. We should continue to see this lead decline. So again, theoretically, the amount of treatment that we might need to do would decline with that over time as the regulations begin to help the private water system owner, not just the public water system owner or public water system customer, I should say. Now, there are still issues with new homes, and this has been a bone of contention. One of the reasons that there were changes made to the regulations was there was the realization that the regulations done in the 80s, late 80s, there was still too much lead that was occurring, especially in fixtures. And in this data, we show that the year plumbing was installed, going all the way out to 2018 for some of the latest homes. And the 2 dotted lines on there showed the 2 regulatory structures there, the late 80s and then 2014. And you can see there's a lot of significant lead concentrations in the 2000s going all the way out until 2016 and 17. We were seeing pretty significant amounts of lead. And the thought there was it was primarily coming from fixtures in this case. And that's one of the reasons that the new regulations really tried to tackle the fixtures and tried to reduce the amount of allowable lead in those fixtures to try to get at this problem of even new homes having significant amounts of lead, at least in small amounts of water that were coming out in the first draw samples. So let's spend the rest of the time now talking about the different treatment and removal options. And the first one being flushing of the system, which whenever I talk to somebody that's got a lead problem, and people in general, they obviously want to know what's the simplest and cheapest thing I can do. Well, there's nothing more simple that you're going to do than just running the water a little bit before you drink it or use it for cooking, right? That's the simplest treatment you could possibly give. Basically doesn't cost any money at all, but it is a habit that you have to get into of flushing the system when the water's been sitting. So as far as running water, it's good because it's easy and cheap. It's bad though because it doesn't address damage being done to the plumbing system. So if I don't treat the corrosive water source of the problem, I'm still going to allow that damage to occur to my plumbing system. So I still may get pinhole leaks in the copper plumbing. I still may get blue-green staining from the copper coming out of the plumbing, but I may be able to at least not drink the copper and lead by running the water. So it's always important to tell people, yes, you can maybe avoid the lead by running the water, but you're not addressing the damage that may occur. The big question, how long do we tell people to run their water for? And it's so individualistic to a home, depending on the size of the home and where you're at in the distribution system of that home. EPA guidance in 2015 said 30 seconds to 2 minutes, which is a pretty big range, but I can certainly show you homes where you don't even need 30 seconds, and I can show you homes where you need more than 2 minutes to flush out the entire plumbing system. We have generally gone, because we try to make things as simple and easy as possible, we've gone to a general 1 minute recommendation, telling people to run the water for 1 minute. If they still get a high lead concentration, one of the first things we might try in that case is to tell them, okay, let's try another sample, but let's run it for 2 minutes or 3 minutes and just see if it was just an issue of not running the water long enough. And the vast majority of the time that takes care of the problem. And those people then know that they have to run the water a little bit longer than the typical person might. Again, this is a lot more difficult in public water system areas where you have to worry about lead mains, and sometimes where you start to get more lead as you're on the water, you'll get slugs of lead coming in from certain parts of the plumbing where even running the water may not be a solution at all. But ultimately, this has to be confirmed through testing. You can't rely on this. So we always tell people, try running the water for a minute and collecting a running water sample. Let's compare those. Most of the time that does it. If it doesn't, let's try running the water a little longer and see what that result is. And almost all the time that takes care of the additional lead problems. And then you every once in a while run into that case where they're still getting high lead, and sometimes we have to do a little further investigation to find out. But it's a perfectly good way to do things, especially for folks who just can't afford to get into treatment. And what we have found in our research is that 1 minute flushing reduced lead, reduced the concentration in 92 to 99% of the cases, depending on which study we look at. It's been anywhere between 92 and 99% of lead levels reduced just based on 1 minute of flushing by private water system owners. If you just look at people that have lead above 15 parts per billion and separate them out and look at what's the effect of flushing the lines for those people, in our research, it's been about 93 to 95% of those cases can be reduced down below the action level. But there's more data to show on that here in a moment, why it's maybe important to look at other aspects of that. If you're interested in more information about flushing guidelines, there's a really great paper. I've got the URL listed on here and the citation for it if you want to look it up. It was done in 2018, looked at the effectiveness of prevailing flush guidelines to prevent exposure to lead in tap water. It looked at municipal supplies as well. It was in the International Journal of Environmental Research and Public Health. So that's a good place to go if you want to look more specifically at flushing water and reducing leads, particularly in municipal systems as well. Now, if we look at the private water system data that we have, this is looking at first draw lead versus running water lead. And anything above that 1-to-1 line would indicate that we've reduced the lead down. Anything below it would indicate that the lead actually went up in the running water sample. And so what we see are a lot of samples down here where they have fairly high first draw lead concentrations, but very low running water lead concentrations. So that's kind of what we would expect in a corrosion situation where we're drastically reducing that concentration by running the water. We do see these occasional cases out here where lead goes up after running, and those are on a case-by-case basis. We have to go in and try to work with those homeowners and figure out, why is that occurring? Is it just not that we flushed correctly? Were we getting some sediment out of the pressure tank that had some lead particulate in it? What was it that caused that increase? Thankfully, that's fairly rare though. For the most part, running the water drastically reduces that lead down, again, in 95% or more of the cases. But there is an important caveat with this. Not only are we not addressing that corrosion problem and the damage done to the plumbing system, we also have to look at how much are we able to reduce that lead down by flushing the sample. So this, again, is looking specifically at samples where the lead level was above 15 parts per billion in the first draw, and then we flush the sample out for 1 minute. What is the resulting running water lead concentration? And in 62% of the cases, the resulting lead was below detection, less than 1 part per billion, which is good. But the problem is 38% of the cases still had detectable amounts of lead. above the goal of 0 parts per billion. So that's a particular concern if we're dealing with young infants in the home or children in the home, where we really don't want to have any amount of lead at all. Running the sample wasn't enough to get it down below detection. And that's a case where if there are children involved, for sure, we might say, maybe try running it for another minute and let's see if we can get that down even further. Or do we really have to go to something like an RO unit or a carbon filter or something to really remove all of the lead, because we just can't flush enough of it out by just running the water. We can get it below the action level, but we can't get it down to really what we'd like to see, which is no detectable amount of lead. So there's good and bad with flushing. It's definitely, I would say it's what most people choose to do just because they don't want to spend the money on treatment, and they're okay with flushing the sample because, most people by habit, when you go to a spigot and you're going to get a drink of water, most people do tend to run the water. They want to get good cold water, so they'll run it for a while. So by habit, a lot of people do that anyway. Even if they don't do that by habit, we'd suggest flushing the water in the morning and then filling up a pitcher with water after you've flushed it and put that in the refrigerator. And then you don't have to go out every single time and flush the tap before you drink the water. And we wouldn't recommend that anyway. Usually we'd say if the water has to sit in there for at least an hour or more before you need to flush the plumbing out again. Well, let's look at corrosion control as another potential way we can remove lead. And we've already talked about corrosion being the predominant source, and we've got lots of research that shows that, and there's tons of research nationally that shows that corrosion is the primary method. These are just some studies that we've looked at. The first one showed a very strong statistical correlation between blue-green staining and lead, which is a classic symptom of corrosion. Another study, we found statistical correlations between the type of household plumbing, the chemistry of the groundwater, and the amount of lead. And we found in that case, 83 out of the 84 homes that had high lead, we could definitely say were coming from corrosive water. There was only one that was even questionable about whether it was corrosive water. In the most recent study, we found 96% of the homes that we were able to correlate specifically to corrosive water. So there's absolutely no doubt it is the predominant source of the problem. And when we look at relationships between things like the LSI index on the horizontal axis here and the amount of first draw lead, you see that the vast majority of the samples, first of all, are corrosive. Keep in mind, a corrosion index in this case of negative 0.5 or less is corrosive water. So that dotted line on there, that vertical dotted line, shows anything that's corrosive. Anything to the left of that is a corrosive water supply. And you see the tremendous magnitude of samples that are corrosive to begin with. But you also notice that almost all the high lead concentrations are associated with that corrosive water, but not all. You do notice a few on the right-hand side of that dotted line. And in those cases, we often have to look at things like that chloride sulfate mass ratio, see if we have galvanic corrosion occurring in the absence of a calcium carbonate problem. So there's all sorts of little intricate details, and you often have to deal with lead problems case by case because there are so many complexities to it. But as a generalization, we can definitely say that corrosion is the problem. So how do we do this? How do we treat corrosion? We can reduce it by reducing the corrosion and stop the plumbing corrosion from occurring. And the classic way of doing that is with an acid neutralizing filter, which is typically just a big tank filled up with calcite or limestone chips, some sort of alkaline material that the water trickles through. It dissolves that material and it raises the pH, raises the alkalinity and the hardness, and reduces the corrosivity of that water. So it's a very simple treatment device. You just need to replace that alkaline material maybe every 6 months, every year. Just depends on how corrosive the water is as to how frequently that tank material has to be replaced. So it's very simple, easy maintenance. One of the side effects is you get an increase in hardness, which can be a problem. Some people that are used to very soft and corrosive water all of a sudden have harder non-corrosive water, and they don't like the hardness. So you'll see sometimes that they'll install a water softener after they put in this. I hate to see that because you have two treatment devices that are fighting each other, and you really don't want to get into that, but we do see cases where that happens. There can also be problems with these if you have metals in the water. It may file up the bed of material you have because you're starting to oxidize some of the metals out, and they'll start to coat the alkaline material, and you'll start to reduce the effectiveness of the corrosion that you're getting from the filter. In severe cases, we can use things like soda ash injection, where we'll take a feed pump and inject a slurry of soda ash directly into the water line. More maintenance here, a little bit more tricky, a little bit of hazardous material. Got to be careful with soda ash. But where we have really corrosive water and an acid neutralizing filter just can't raise the pH enough and can't get that corrosivity index up high enough, we can use soda ash instead. We increase sodium in this case instead of hardness, which is a concern for some people. And there's definitely more maintenance. These are a little bit more tricky to deal with, and they're not preferable for sure. The acid neutralizing filter, people I've talked to that have had both of these would definitely say that the acid neutralizing filter is a much preferable route to go if it'll work for you. And this is a typical situation of what you see when you install an acid neutralizing filter. The before filter is on the left, and we notice a pH of 6.07, and we have a corrosivity index negative 3.2, so very corrosive water. We've got almost 7 milligrams per liter of copper in the first draw, and we've got 13 parts per billion of lead. So a pretty significantly corrosive water. And after the acid neutralizer, we have a pH of 7.84. We've got a little bit more hardness now. We're at 81 milligrams per liter. The pre-filter was much lower hardness, but we notice we have no lead, no detectable lead, and our corrosivity index is now non-corrosive. It's negative 0.08. So in this case, the filter worked beautifully. It raised the pH, got rid of that corrosion index problem, and brought our lead level down below detection. And so now we're protecting the plumbing from leaks, and we're not dissolving lead, we're not dissolving copper either, at least not enough to worry about. And we've been able to solve the problem just purely through corrosion control. What we see, however, is that those systems are not installed very frequently. In Pennsylvania, we find only about 1 or 2% of people have an acid neutralizing filter, despite the fact that corrosivity is about 60% of the private water supplies. Water treatment is focused very much on aesthetic issues like softeners and sediment filters, and much less so on health issues like bacteria with UV lights or RO units or chlorine systems. So that's one of the real disconnects we have between treatment and problems, is the treatment is very focused on aesthetic problems because they're visible and people can see and taste them, and less so on some of those health concerns. You will notice things like RO units are a little bit more common, and also faucet filters, which tend to be carbon filters, as well as larger carbon filters, are more common, thankfully, and those will help to deal with some of the lead problems. We get questions all the time about, well, I have a water softener, so I don't have a lead problem, because water softeners take everything out. Well, softeners do a lot of things, and homeowners definitely believe that they will remove lead, and they will remove some lead. They're a cation exchange device, and lead is typically a cation. So you can get some lead removal from source water, but the problem is most of the lead's coming in after you would put a softener in anyway. So it doesn't address that major issue with corrosion of lead. And in fact, a softener by definition can make the water slightly more corrosive too. So it's really not going to be the answer to our lead problem, because most of our lead's being generated downstream of that softener anyway. We need to look at other types of devices that can actually remove the lead. And not to mention the fact lead's not easily removed from the resin once it attaches either. So it's definitely not the ideal solution, not even a preferable solution at all. Some of the other treatments that we have, first of all, we get asked the question about, what about sediment filters? People have this feeling that, oh, lead is heavy and it's a big particle and it's a sediment, and we can just remove it with a physical filtration process. And there is some truth that particulate lead can be important in some cases. But what we found, this was a graph from a study we did in the 90s, where we looked at particulate and dissolved lead and found that the vast majority of the lead was dissolved, but on average, particulate lead added anywhere from 6 to 20 parts per billion into a typical sample. So it was appreciable, the amount of particulate lead that was there. And any kind of sediment filtration could help with that. Again, the problem though is we put a sediment filter in where the water comes into the home, and a lot of this particulate lead might get generated by the plumbing system as particles of solder coming off downstream. So again, we might not address even some of the particulate lead that comes in after a sediment filter is installed. So there's obvious problems with this. It's certainly not going to hurt, and sediment filters are always a good idea. They're somewhat underutilized really in water treatment because they're so simple and can provide a lot of good benefits. And filter sizes vary anywhere from 1 micron up to hundreds of microns, but typical ones 5 micron and 20 micron, you're going to probably get some small effect, but it's definitely not an answer to a typical lead problem, and you're going to have to replace these filters about every 2 to 3 months. Carbon filters are an interesting one because they're used for a lot of different things. They're used for odors and tastes, various organics, pesticides. You can use them for metals. You can use them for radon removal. So they have a whole host of different uses, but they come in many different ways, right? You have small faucet filters, you have under sink filters, you have large tanks that are whole house, you have pour through carbon filters. So lots of different kinds of them, and they're definitely not all created the same. So generally speaking, solid block tend to be better, especially for lead removal, as opposed to granular carbon. But there's even distinct differences between solid block under sinks and then faucet filters. And there's subtle differences between all these. And you really need to look, first of all, at certification, making sure that they're NSF certified as a carbon filter for lead removal. Some of the advantages of these, they're relatively easy and they're cheaper than a lot of other treatments, particularly something like reverse osmosis. But some of the things you have to be aware of is that water quality is important here, right? There can be other things in the water that exhaust the carbon, and we have to be concerned about that. Is the carbon going to get exhausted by something else in the water other than maybe just lead? Is there an organic present? Is there chlorine if it's a public water supply? What else is going to be removed by this? And how often do we need to change that filter? And that's always the difficult question. How frequently to change the filters, and are people going to change the filters? One of the most common problems we see is people don't maintain these devices. They leave the carbon filter in place for a year and 2 years. And if you do that, the problem is you can get worse water quality than is going into the filter. So you really have to maintain them and really have to harp on people to change these filters routinely. At least 6 months is preferred, if not more frequently than that. And you also have to realize, depending on where a carbon filter is, you may have lead components after that filter. Even an under sink filter could have issues with small amounts of lead coming from the faucet itself after the filter. So we still have to deal with things like maybe needing to flush the water a little bit, even if we're using a carbon filter. And there is a really excellent paper. I just got an email the other day from Riley Mulhern. I think that's how you pronounce Riley's name. And he's a PhD student at North Carolina Chapel Hill, did a really excellent paper on the use of under sink activated carbon filters to remove lead. And so the citation is listed here. They found really good removal, 98% removal among 17 homes over 6 months. And these were under sink solid block carbon filters. And they worked even at really low pHs, which is one of the concerns about carbon, is that maybe they don't work as well on lead at low pH. And in this case, they did work very, very well. So that's an excellent paper that just came out recently if you want to look into more about carbon filters. Carbon holds a lot of promise, again, because it's simple and it's relatively cheap. So especially in areas of low income, carbon can be a really good source to try to reduce lead levels down in both public and private water supplies. Reverse osmosis filters, I know they've been dealt with in other aspects of this series of treatment webinars, and they have a lot of utility for a lot of different things. They remove a lot of different things at very high efficiency rates, typically 99% or more for lead. The downsides of them, they use a lot of energy to force water through a membrane. They waste a lot of water. So they're not the best thing. I mean, they have other issues, and they also may need a lot of pre-treatment. Keep in mind, a lot of RO filters will have several pre-filters to try to get rid of sediment and use carbon to reduce things like some of the metals that may be easier to remove before they go through the RO filter. So some pre-treatment might help, but very efficient units, not the cheapest things though, especially compared to a carbon filter. You can get into significantly more money with an RO unit, and again, wasting a good bit of water to produce it. You can even do whole house RO filters, but certainly wouldn't need to do that for just a lead problem. And then finally, distillation units. We very rarely see distillers used anymore. They were kind of trendy back in the 80s and 90s. We saw quite a few of these, but it's actually been a long time since I've talked to anybody that has used distillation, but it's perfectly fine. It's got a similar efficiency to reverse osmosis, where you basically heat the water, condense the steam that comes off the boiling water, and you're basically just collecting pure water and whatever might move with the steam. So one of the disadvantages of these are light organics that boil off before and would come out in the steam. So you would actually condense those and have more in the condensate. So you have to watch a few things. Those are rare problems though. For the most part, distillation units have really high efficiencies. They are energy intensive. They don't produce a lot of water, but they can produce extremely clean water, which is a very big advantage of them. And they're certainly a possibility if you're dealing with a lead problem and you want to try to remove that lead. But we have to remember our goal ideally is to prevent the lead from even occurring. And that's really what I always try to talk with people about is let's figure out how to stop the lead corrosion preferably and try to deal with that as opposed to just removing the lead after it has come out of the plumbing system. So corrosion control is great. Again, it's not cheap though. We might have some cost prohibitive issues there, but it's really better if we can to try to control the problem before it occurs. So in summary, we've got regulations that are helping to slowly reduce lead over time, and hopefully lead treatment will become less and less of an issue as time goes on. This lack of awareness is a critical hurdle though. We've got to have more people in private water supplies testing their water to see if they do have a lead problem. We know that plumbing is the predominant source and source water lead is very rare. And so things like replacing plumbing systems or corrosion control are the preferable route, but they're not cheap. Simple and cheap treatment can be running the water, but you have to realize you may not reduce the lead all the way down to the detection level, which is where we'd like to be. And that leaves us with things like point of use carbon filters, RO units, and distillation units, which give us really high efficiency at varying degrees of cost, but can work very effectively at producing very clean water at the tap. So with that, I will be happy to answer any questions you might have.
Great. Thanks, Bryan. Appreciate the insightful presentation. We have received a series of questions. So Philip asked a question, what's the typical geologic composition in Pennsylvania?
Well, we're dominated by sandstones and shales, and so we do have a lot of relatively acidic. So I would say the average pH of groundwater here is slightly less than 7. We have quite a bit of soft water, especially across northern Pennsylvania. And so when you add slightly acidic and soft water together, that's where we get so much corrosive water in this state. We do have some pockets of limestone, which obviously produce the direct opposite. We have a lot of hard water areas. I live in one of those hard water areas where we don't worry at all about corrosion here. We have tremendous scaling problems, but a lot of the state does have acidic sandstones and shales, and there are some sand and gravel aquifers as well that can produce some pretty corrosive water.
Great, thank you. Kristen asked, how frequently do you recommend a private well owner test their drinking water for lead?
Well, I think you always start with one, right? You just want them to test that one time first. And there's not a lot of reason to believe that lead's going to change a whole lot. It's not like bacteria that changes with weather. As long as the other chemical nature of the water, the corrosivity of the water is not changing tremendously, and you're not changing the plumbing system, we would expect it to be fairly constant. So we try to get that one test done and go from there. If they have a problem based on that one test, then we might recommend more frequent testing thereafter. But it is one of those parameters that maybe if you could just get it tested once and show that you don't have a problem, it might be something you do a few years later just to make sure that it wasn't an improper test.
Great, thank you. William asked to explain the galvanic corrosion again, if you could, please.
Yeah, and galvanic corrosion is something I've never understood very well, honestly. It's a dissimilar metal corrosion that occurs. It gets deep into chemistry, which I'm not good at all on. So I would suggest you research that one online. USGS has a really excellent corrosion website. If you just Google USGS corrosivity in water, they've got a really nice site that describes the corrosion indices and talks more about corrosive water. But galvanic corrosion is incredibly complicated, and I do not understand it well. I'll admit that. Be the first to admit that.
Thanks. Haley asks, does high turbidity play a role in corrosive water, or is it more connected to alkalinity?
It's much more related to alkalinity. Temperature plays a role, but really turbidity is not much of an issue. It's really water. The easiest way to think about standard corrosion is it's water that wants to dissolve things. And the more dilute the water is, the more it wants to dissolve things. So there's probably nothing more corrosive than rainwater, because rainwater is acidic and it's got nothing in it. And it just wants to dissolve things because it's got nothing in it. Whereas when you're dealing with deeper groundwaters that start to dissolve rocks and minerals, that's where the corrosivity kind of goes away, because it's not nearly as dilute, not nearly as acidic, and it's not searching out to dissolve things anymore. So really, it's primarily because of the softness of the water, the slightly acidic nature of the water, the dilute effect of that water wanting to dissolve whatever it comes in contact with.
Great, thanks. Alan asked, given the large number of private wells in Pennsylvania, as shown on the map, why are there no state regulations for private wells in Pennsylvania?
We could do a whole webinar on that one. You know, it's honestly been a political issue. That's all there is to it. It has been viewed, first of all, it has been submitted many times, and it has been voted on many times. And there have always been different interest groups that have fought it. And those interest groups have actually changed over time. Some of the ones that used to fight it now are in support of private water well construction standards, and vice versa. It just ebbs and flows. And most recently, it's mainly been groups that think any government regulation is bad. And those are the groups that have fought it. There's really no merit to the fighting it. It's just the fact that anything that is government regulation is bad, and therefore we're going to fight this regulation. And so while most states consider this common sense, that we should regulate the construction of something that is tapping into a public good, right? We have not gone that route. We have decided not to regulate them, and it's purely been political.
Got it, thank you. Sandra asks, what were the private well owners aware of about the pH of their water? Were they aware that the water was more acidic?
I'm not sure. I guess we're going back to that awareness graph where pH was maybe like 18% or something like that. And yes, although well owners are also aware when they have high pHs as well, because that produces some very characteristic taste to the water and some other features to the water. So I would say they're equally aware. The thing is, we have very few cases where pH is high in Pennsylvania, above 8.5, but we have lots of cases where it's low, below 6.5. And in those cases, what they're basically aware of is the corrosivity coming from the low pH. One of the common misconceptions, though, is people think pH and corrosivity are the same, and they are definitely not. pH is a component of corrosivity, an important one, but it's not the only one. But yes, when they're aware of low pH, they're mainly aware of corrosion problems.
Got it. So Mary has a comment and a question. In Ohio, local health districts were told that we have to be lead risk assessors to collect lead water samples for private water supplies. Is this required in Pennsylvania?
No, we have no requirements in Pennsylvania of anything. So we don't even require location or construction standards on wells. We have no testing requirements on wells. The only testing requirements are in a couple of different counties. We have 67 counties, and we have just a handful of counties that have passed standards that actually include some sort of testing, and that testing is mainly done during a real estate transaction or when the well is drilled. That's the most common time. And other than that, there's no testing done on private water systems other than what a homeowner chooses to do or a buyer or seller during a real estate transaction.
So let's wrap it up with one last question, Bryan. Is based on all the work that your program has done on lead outreach and awareness, what are some of your big takeaways, recommendations for risk communication with regards to lead?
Well, I think my big takeaway is when you look purely at health effects, you can make the argument that there's maybe nothing more dangerous than lead in water, especially toward infants and young children. And so you have to argue to people's sense of their family and say, you know, maybe don't think about yourself, but think about your kids and your grandkids. And there's nothing more harmful to kids than lead. And so the big hurdle is getting them to get their water tested that first time. And you have to argue with them about children, and please be concerned about your children. This is not a rare issue. It's still occurring in maybe 10% of private water systems, which when you're talking 1 million private water systems, that's 100,000 homes just in Pennsylvania that may have a lead problem. And how many kids are we talking about in that case too? So unfortunately, unless there's some very obvious corrosive copper symptoms like blue stains or pinhole leaks, they may not think about lead. And so it's really that big hurdle of getting them to just get that water tested and argue with or appeal to their sense of their family and especially their younger family members.
Excellent. Thank you so much, Bryan. Thank you for all the insights. I know some folks ask questions regarding the presentation. Will it be shared? We will be sharing the recording to this webinar in a follow-up email, along with all the links that Bryan referenced during his presentation. As far as CEs, there will be some instructions on how you can get those logged in as well. And with that, we're almost out of time for today's webinar, so I'd like to wrap things up. I want to thank Bryan again for his time and sharing his expertise on lead safety and treatment in private wells. I want to thank all the attendees for being engaged, asking questions. As a reminder, please do not forget to take the survey that will pop up as soon as you log out of this webinar. Your feedback is very important to us, and it helps us plan for future events. And with that, thank you again for joining us, and we will see you next time. Thank you.